Okay, please close your laptops. We begin rolling motion today, and for you guys, we finish it today too. So, because we have an extra lecture at 4:30. Yeah? You have a makeup lecture, right? And then we have the review session tonight as well. So please close your laptops one more time. Laptops. If it's not physics on that laptop, please close it. Yes. Yes, 7 to 9. All right, so guys, we need to develop basic relations for rolling motion. And beginning with, what does this stand for? I mean, I've said it up here. This is an object rotating about a fixed axis. Okay, this center of mass is, how do you get this? This is like getting your bicycle, putting it upside down, and spinning the wheel, the front wheel, about its axis. So the center of mass speed is 0. And if that's not physics on the laptop, please close it for fairness. You doing physics on it? Okay, I believe you. So the center of mass speed is 0 because this is fixed, rotating about a fixed axis. And the angular speed is omega, so it just spins this way. The second extreme is when you have an object moving. The center of mass is moving, but there is no rotational motion, and we call that just simply sliding. And the third example is when V is equal to omega r. The speed of the center of mass is given by omega r. We'll talk about that in a second. We call that ideal rolling or rolling without slipping. Now, I'd like to establish some ground rules or some basic relationships between speeds of points, center of mass, top and bottom. What would the speed, if this is a wheel spinning about its center of mass axle through center of mass, what would the speed of the top be? What did we say? Something. Tangential speed is equal to what? V equals to omega r. What about down here? V equals to negative omega r. And VCM is 0. This is, again, rotation about fixed axis.
Why negative omega r?
Do not speak without putting your hand up. First, Kevin. Yeah. So if we pick that direction to be positive, that's omega r, and this is negative omega r. Not now. Give me a few minutes, and you can ask your question. Okay, guys. So I'd like to establish with you a few ground rules as to, we call this V top, okay, and this is V bottom, and this is VCM. Bear with me, please, and on a sheet of paper, please write down the following. V top equals to, bear with me, VCM plus what? And then V bottom equals to VCM plus what? Whatever, plus or minus. Okay. It's obvious. One is 0, one is, what am I saying here? V top is VCM plus omega r, and V bottom is VCM minus omega r. And I conclude from that V top is equal to V bottom plus what? 2 omega r. Okay? If we take derivatives, we can also prove or show that, please pay attention, A top, the tangential, TT, tangential top, is equal to ACM plus alpha R, and A bottom. The little t up there is for tangential, tangential acceleration. That's equal to ACM minus alpha R, and A top tangential equals to A bottom tangential plus 2 alpha R. I'm just dividing by t these equations if you want. That's one way to see it. All right. So this is for an object. As a matter of fact, guys, the equations that I have on there for you, they hold for a disk that is spinning about a fixed axis, but they also hold for any object where there is rotation involved. The speed of the top is related to the speed of the center and the bottom in this fashion all the time. Now the speed of the center of mass might be different from zero, but these things will hold for everything that we deal with. Now for the first time, we're going to make a transition from rotation and translation into study of an object that is actually rolling, ideal rolling. Let's say you're driving on the 401 at speed limit 150, and what is the speed? Please pay attention now, guys. Your car's speed is what? 150. What is the speed of the center of mass of the wheel? Also what? 150. What is the speed of the part of the wheel, of the tire, that is in touch with the ground? What would it be? Common sense. The speed of the part of the tire with respect to the ground. The part of the wheel in touch with the ground relative to the ground. What would the speed of that as it touches the ground, that point on the bottom? What would the speed relative to the asphalt be? If it's not zero, what do you expect to see? You see skid marks. Either it'll be spinning. Please pay attention. This is a key point for rolling motion. We have to come to an agreement that if a wheel is rolling on the ground, this is not mathematics, it's not physics, it's just common sense. If a wheel is rolling on the ground and there is no spinning, there is no rubbing between the wheel and the ground, and there's no skidding, also there is no rubbing, it is not leaving skid marks, the asphalt is not eating away the rubber, then we have to have the speed of the bottom of the wheel or the point on the wheel in contact with the ground must be zero relative to the ground. If it is not, then we have either skidding or spinning or something like that. Okay? So if that's the case, guys, this is ideal rolling. So this is an object executing ideal rolling. And by that I mean no skidding and no spinning. This can be summarized by saying no slipping. Okay? If you have that, then if this is the case, then we have established or agreed at least that point bottom, V bottom must be zero. If that is the case, please write down what the speed of the center of mass will be. These formulas hold for everything that spins or rotates. They will hold for an object that is rolling too. If the speed of the bottom is zero, right? What would the speed of the center of mass be? Omega R. What is the speed of the top is going to be? Look here, that'll be what? 2 omega R. So V top is 2 omega. By the same token, if this object is not only undergoing angular speed, angular motion, but also accelerating with angular acceleration alpha, then we can say that if there is also alpha on top of omega, okay, so it's accelerating this way, I could say that A top is 2 alpha R and ACM is simply alpha R. Okay? So these are key conclusions so far. The A, the center of mass, is alpha r, and A at the top is twice as much to alpha r. Same thing holds for the speeds as well. Let's think a little bit now. I am sitting in my car, driving in that direction. Please pay attention for a sec. And the car is in gear, driving that way. I hit the gas pedal. So I'm driving that way. I hit the gas pedal. What will happen? Which way will the force of friction be on me? Again, on my car, or on the wheel. I'm sitting here driving that way. I hit the accelerator pedal. Which way is the force of friction going to be on my tires? That way or that way? Who's for that way? Who's for that way? Now imagine this, guys. What happens when we're driving that way? What happens when you hit the accelerator pedal? The axle grabs the wheel, and which way does it twist it? It turns it this way. What is the wheel doing to the ground? It's pushing the ground backward, and then the ground is pushing the wheel forward. As a matter of fact, another way to see it is, guys, what is the only force acting on the car, external force acting on the car? It's friction, a force of friction. If there is no friction, we're going nowhere. It can't accelerate or decelerate, right? And because of Newton's second law, because F equals ma, and A is that way, the car is accelerating in that direction. Since the only force acting on us is the force of friction, the force of friction must also be in that direction. Okay, now I slow down. I hit the brakes. By the same logic, if I hit the brakes, first of all, what force acts on me? Is it kinetic or static friction? I am moving, but we have established that the speed of the wheel or part of the wheel in touch with the ground relative to the ground is zero. So static. Okay, we don't want it to be kinetic, as a matter of fact. Okay, we'll talk about that maybe next lecture. So if I hit the brakes, which way is my car? I'm moving that way. I hit the brakes. Which way is my car accelerating now? That way. By Newton's second law, the force of friction must be acting also backwards on me. What is the difference between static and kinetic? If you hit the brakes too hard, what will happen is the wheels will lock. So you go from static to kinetic, which is not good because kinetic friction is a lot less for things like snow and ice than static friction. So what ABS systems do is they try to keep you at the point of impending sliding. Okay? They pump the brakes for you, so when you're about to slide, they let go. About to slide, they let go. Why do they do that? What you're trying to do is keep the force of friction, which could be anywhere between 0 and Fs max. Okay, when you hit the brakes, the force of friction will increase until you hit Fs max, and then you slide. They try to keep you in that region where the force of friction is Fs max. Fs max means you're about to slide, but you don't slide. So what did you do before ABS systems were around? Whoever of you was, you were the ABS, manual ABS, or ped ABS. All right, so just a few things about rolling motion, okay? Before we move on, I want to demonstrate to you a few things here. This is from last chapter, by the way, a few things from last chapter. This is called the moment of inertia machine, okay? And what this beast will do, hopefully, is... Sam, can you see this? These guys are unbelievable. They put these things here, they don't move. Move. What the heck? All right, please pay attention now, guys. I'm gonna put a weight on the side. Wait. You'll be saying whoa, but not yet. Shut up. All right, so guys, this is a weight. I'm hoping not to break anything here. All right, so I'm gonna let it go. Please pay attention and see how fast it will go. It's not that fast, but it's going. All right, so Okay, see how, okay. Now, these are point masses. I'm going to move them from almost r equals, you saw how fast that went, right? I'm going to move them from almost r equals 0 to r equals big, whatever. All right. Ravid is thinking, is it going to be that easy? No. You're not doing this. Okay, now that we have changed, masses are the same, all I've done is change the geometry a little bit. Let's see how fast this will go. Same way, same. A moment of inertia is different. It takes a lot more to accelerate this than before. This is the moment of inertia thing. I don't want to put my finger there. This is not a good idea. Okay? It's not a very bad idea either, but just, you know. All right, so you see that this is the moment of inertia little demo here. Okay? Okay. So that's that. So you have a ball, or let's say no ball. Say it's a cylinder or a disc of mass m and radius r. It is rolling downhill, and the hill has slope of angle theta. What I'd like you to do is draw the free body diagram of the disk and also write down the equations of motion. What we are aiming for is to find the acceleration of this object down this way. What is ACM equal to? Also, please pay attention to this point. There is friction here. There has to be friction, otherwise we will not roll, right? The question will also likely ask you what the force of friction is on this thing. What is the force of friction? Some of you, or some of us will run away and run, say assume that the force of friction is equal to N mu S, okay? We can't do that, why? When is it equal to N mu S? When it's about to slide, or it's about to, if there is no impending sliding or skidding, we cannot assume that the force of friction is equal to N mu S, okay? So please write down the free body diagram and the equations of motion for this object as much as you can. We've never done anything like this yet, so. All right, guys. Forces acting on this thing are what? Right away, we have the normal from the ground, N, and mg already broken up into mg sine theta and mg cos theta. They have to act here because center of mass forces. And also what? There is a force of friction. Do you know which way the force of friction will act? Should it be down or up? Who's for down? Who's for up for the force of friction? Why does it have to be one way or another? Can you prove conclusively that it has to be one way or another? Guys, can you think of why it has to be absolutely one way and not the other for this object?
Otherwise, it's going to roll.
Um,
Like if it was going down, why would it roll?
I need physics proof. Very cute. Please focus here. This object was not rolling before, stationary, and suddenly it started to rotate. Okay, which way is the angular acceleration? Has to be this way. All right, let's go now and and I lost my my mic. Hold on. I know how to do this. Ooh. See, I'm evil. Yeah. Sorry. I'm so bad. She's got the earphones on. I'm such an idiot. Sorry. By the way, this is wonderful, guys. I wear it between now and March. It's good till April. It's natural, not alpaca wool, but something else, and it's really keeps you cool in the spring and keeps you warm in the winter. Do you know the Shmoo? Anybody know what the Shmoo is? Shmoo. Look up the Shmoo. It's from the movie. Those of us who are a bit older know it. You should see that movie, by the way, guys. You'll appreciate it. Lucky number 11. And you don't know the Shmoo? The Shmoo is in there. Anyhow. Okay, guys. So we know that alpha has to be this way. Angular acceleration, okay? So let's examine from the point of view of the center of mass. Now, this is the center of mass right there. What forces exert a torque about the center of mass? I need a demo. I need a volunteer. Just a quick one. Nothing from far, just close by. Anybody? You. Move it. Thank you. Arm out. This is center of mass right there, okay? This is the normal force. Is it generating rotations about the center of mass? No, the torque is what? 0. How do you find the torque of a force? This is the force. How do you do that? This is the force down. You find this is the force right there, okay? Pushing down like this. Like that, okay? So that's how do you find the torque of a force? You extend the line of action until you find the perpendicular distance, and that's, okay, so you have to find the perpendicular distance. This is the force here, there is torque there, non-zero. Okay, what about here? That is acting there. Where is, guys, this is the center of mass pivot. Where is the moment arm? We call this distance, the perpendicular distance, we call it the moment arm, okay? So that's the moment arm. The perpendicular distance. For this force, what is the perpendicular distance to the pivot? Extend it, it's right into the pivot, it's 0, right? So if I pull it, thank you. So, please, the pivot is here. Center of mass pivot is there. So, guys, what is the torque of mg cos theta about the pivot? 0, right there, right? Mg sin theta about the pivot? 0, no rotation, right? What is the torque of n about the pivot? Also what? How do you find that? You extend the force till you find the perpendicular distance, and that's 0. 0, 0, 0. None of these is creating torques about the center. Okay, fine. Do we have to have a torque about the center of mass? Yes. Why? Because there is alpha. And we have a law that says torque net equals to I alpha. And the torque and alpha have to be parallel. So now there is only one force left that we haven't counted for, which is the force of friction. The force of friction must be that way. Why? Why, guys? Because look at the center of mass. Okay, where is the force of friction there? Which way is the torque from the force of friction about the center of mass? It's going, what does it do? It twists, right? So you go from the center to the force and you see which way it twists you. The torque from this is this way. That is tau, and that is parallel to alpha, so it has to be in that direction. No questions yet. No questions. So the force of friction must be acting up to cause this thing to roll. Give me a few minutes for questions, please. Okay? So now we know that the force of friction is up. Next, I'd like to write down the equations of motion. Sum Fx equals to max. What are these forces in the x direction? I have mg sine theta minus the force of friction for static equals to MACM. How many unknowns do I have? What do I not know? The force of friction and the acceleration. Then we have two unknowns, A and the force of friction. We need one more equations. I've seen your hand up. I will deal with you in a couple of minutes. Please put your hand down. Sum F equals to MA. Fine. We have two unknowns on one equation. Guys, obviously, this is not going to do. Why? Because this is not only a sliding problem, it's a rotation problem too. So we need sum of torques. So second point is sum of the torques about center of mass is equal to ICM alpha. Okay. Sum of the torques. What exerts the torque about the center of mass? Does this? No. Does that? No. Does that? No. None of these are able to generate rotations about the center of mass. Okay, so we have to use the force of friction. Says that, what is the torque of the force of friction? Distance times F, perpendicular distance, RF equals to ICM alpha. And then what? R times F equals to, what is ICM for a disk? M R squared over 2 times alpha. This is equation 2. What is my equation 3? How many unknowns do I have now? A, F, and alpha. Finally, ACM is equal to what, guys? Alpha R. So third equation is ACM equals to alpha R. Okay, my advice to you is, how do you deal with a three unknown system? Substitute everything where? Into what is the key here? The torque equation. Okay? So alpha must go in there. And the force of static friction must go in there. You isolate for it here, and you bring it down there, and put it here, and then you end up with an answer for A. Okay? So how do we do this then? Let's do that. R times the force of static friction from 1, the force of static friction is mg sine theta minus MACM. Okay, that is RF, that part, equals to mr squared. Please pay attention, guys. The R should all be the same. We're dealing with the same radius, so just being sloppy. mr squared over 2 times alpha is ACM over R. Please pay attention now. I will divide by, cancel R, divide by R here, and divide by R there. The R's are gone. Divide by R, R's are gone. And also divide by M. The M's are gone. And you end up with ACM equal to what? Help? If you do that, it says basically 3/2 ACM equals to G sine theta, and ACM is equal to 2/3 of G sine theta. So guys, what is the force of friction equal to? How do you get that? You substitute, I don't know, whatever you want. Substitute A here, there, and you get that Fs is equal to, anybody? 2/3, 1/3, 1/3 of mg sine theta. Okay, guys, I apologize for, I don't apologize, I don't care. I won't be answering questions now because we have a few things to do and we have people to deal with, to bring up to the front and deal with.
Like me?
Not you, just shit. I said shit back there. I meant to say sit back there. Sorry. Okay, so People, remember that tau net equals to what? I alpha. Also, tau net equals to, what did we say with respect to angular momentum? Tau is equal to dl by dt. Please pay attention here. Angular momentum is a vector. Which way does it point? For example, I have this disk here. Look at that. Or wheel, okay? Please pay attention. Which way is the angular momentum on this wheel? It's a vector that follows the right-hand rule. You spin this way, it's actually up that way. Okay? I'm not gonna, if I want to change the speed, what is it saying? If I want to change the speed of spinning, angular momentum is I omega, right? So, what is angular momentum again? It's L is I omega vector. How do I change the angular momentum? I have to apply torque to either do what? Change the amount of the magnitude of speed or the direction of the angular momentum vector. Okay, let's take a look at this. I need torque to speed it up or slow it down. That's what I'm doing. But also it says what? I need torque to spin it this way. Do you believe that? Yeah, it takes force to do that. Okay? So where's my rope?
Is it harder to move it when spinning?
It is. Won't have time to show you. Please pay attention now. Okay, what happens if I do this now? Flop. I'll probably hurt myself, but I don't want to hurt myself right now. Okay, so it just flops, right? Okay. Now check this out. Not yet.
No way.
It takes torque to bring that down. This is not easy to do.
What the hell?
Ravi, come on here. So, have a seat. Okay. Feet on the thing.
Feet on this one.
Yeah, we're gonna do two things with you. One is I'm gonna spin you, okay, and I need you to. I know you know. Yeah, bundle up once, and then as you're spinning, spread your arms out, keeping your composure. Okay, right? So yeah, ready?
Okay.
There you go. Don't hit me. Okay, arms out.
Whoa.
Arms back in. Arms out. Arms in. And the moment of inertia is changing, but the angular momentum is constant. Now I'm going to spin her back to, that works. It actually works. Oh, just hang in there. Okay, get up, let me see. I do that. You're doing good? Okay, sit down again. No, sit back down. Yeah. Hold this, please. Now, what I'm going to ask you to do at some point is, don't be afraid of the wheel. Okay? Sit forward a little bit.
Okay.
And what you're going to do now for us is keeping your composure, your body straight. You're going to go like this and then stop and go like that when I say so. Okay?
So I'm gonna go
No, yeah, exactly.
and then stop.
Stop and go,
here.
yeah, and then go like that, stop, go the other way. Cool? Ready? Hang in there. Okay, foot off the ground.
Okay.
Go like this. Other way. All the way, other way. Thank you. That's conservation of angular momentum. Okay? So, guys, you just saw that for a disk, A was equal to 2/3 G sine theta. What would it be for a ring? What would it be for an object sliding downhill? It is what? G sine theta. For a, what is happening? Why is it slower for an object to roll downhill and slide downhill? Part of the energy that goes into moving it goes into sliding it, but a good portion goes into what? Spinning it about the center of mass. See, it takes energy to spin it, so that's why it ends up going. So if it has a different moment of inertia, then the acceleration will be different down the hill too.
Are we done?
Yeah, we're good.